Algebra 2 at Trig, we're working on exponential growth and decay functions. This is 6A.0. We're talking about Alice in Wonderland and a video we watched where Alice got real small to fit through a door and then she got real big by eating fancy cake. So what we noticed is before she took any sips from the bottle, she was 4 feet tall. So we plotted a point at 0.4. After one sip, she became half the size, which is 2 feet tall. After 2 sips, she was half the size. After 3 sips, she was half of that. And after the 4th sip, she got to her required height, which would be, if half a foot would be 6 inches, a quarter of a foot would be 3 inches. So she's now 3 inches, which is the height that she needed to be to have access to the door. So the equation, write an equation to model this situation. So our format of an exponential is always going to be y equals a times b to the x power. The b value is our common ratio. The a value is our y-intercept, or the point where we are starting. So, what is our y-intercept in this situation? So we have y equals 4. What is our common ratio? What is each y value being multiplied by? For 4 to become a 2, we had to multiply by a half. For the 2 to become a 1, we had to multiply by a half each time. So we have a common ratio of a half. And we do that half multiple times. So we use an exponent x. Notice that this is not the same thing as 4 times a half to the x power. You would multiply the numerator, so 4 divided by 2 is 2. You'd be doubling every time. This is not doubling. This is cutting it in half. So order of operations tells us we have to do the exponents before we do multiplication. So a common mistake are people who multiply that out in the wrong order. Where is our y-intercept? Zero 4 is our y-intercept. Okay, we can tell that by multiple ways. In our equation, if you plug in 0, you would have half to the 0 power. Any value to the 0 power is always 1. So 4 times 1 would give us that 4. On our graph, we can see on the y-axis where x is 0, we're up here at 4, the y-intercept. And in our table, when the x value is 0, we have a y value, or a height, of 4. So this is going to show us the beginning point. When x is 0, what we're beginning our height at. So that is going to be considered an a value. How about our b value? What is our b value? What is our common ratio? Our common ratio in this case is a half. Every time we do a calculation, the x implies that we repeat the half again and again and again. In our graph, you can see that it cut down the previous number to half the size. And in the table, as x increases, the y is decreasing by half every time. So that's a b value being a half. No, I'm sorry. Up here I said a equals 0. A does not equal 0, that's for sure. A equals what? A equals 4. In fact, a has to be greater than 0 to be exponential. A has to be greater than 0. It cannot be a negative number. Mathematically, you can have a negative number in front of the parentheses, but that's not considered exponential. Our b value is a half. So we would have exponential decay if the b value was greater than 0 but less than 1. We'll have exponential growth if the b value is greater than 1. Again, not negative numbers. Mathematically, you could have a negative number there, but that would not be exponential. It would not be exponential growth or decay, at least. What line does our graph seem to be approaching? If we were to connect these and make it graphing a normal function, what line are we approaching? The x-axis. And that x-axis we could never reach maybe by doing our graph. We'd get so close, I'm sure we'd bump into it. But over here in our table, a little bit more accurate data, if it was 5, it would be 1/8, and then 1/16, and 1/32, and 1/64. It would keep getting smaller and smaller and smaller, but you would never reach 0. You'd definitely never become negative. So this is called an asymptote. We did asymptotes earlier with rational equations. The line that your graph approaches but never hits is going to be an asymptote. So we have an asymptote at y equals 0. Because our graph can never hit 0, can never hit the x-axis. That asymptote can change if there was a translation to the graph, as we've had many times in the past. Does this situation represent exponential growth or exponential decay? As we stated before, it's exponential decay, because the b value is greater than 0, but it's less than 1. The b value was a half. The common multiple, the common ratio was a half. So then in our video, she got to the door, she couldn't open it. She had to go back to the table, but now she's 3 inches tall. She can't reach the table, so she needs to grow. So she finds out if she takes a bite of the cake, she may be able to have that help. So in order for Alice to retrieve the key, Alice needs to grow back to her normal size. After each bite of cake, her height doubles. However, after eating the cake, she grows to a size of 16 feet. Apparently, she ate too much. Make a table to determine the number of bites of cake Alice took to increase to this size. Remember, she is at a 3 inches height. So what is that in feet? It'd be 3 inches, but what are you thinking with the 4? 1/4. It's always a trick. So we have 1/4. That's her height in terms of feet that we had on the previous page. If she takes 1 bite of cake, and every cake makes her double in size, how big is she going to be now? Everyone should have an opinion. We're going to multiply that quarter by 2. Remember, when you multiply a fraction by an integer, you multiply the top numbers. So 2 times 1. 2 times 1 over 4. That can be reduced to 1/2. That's twice the size. She takes another bite, and she's at 1. Takes a third bite, and she's doubled her size, and we continue this pattern. So after 4 bites, that's perhaps where she should have stopped. But if she grows to 16 feet, she must have taken 6 bites. This was our multiplier, our common ratio. And if we plotted those points, we started out at 1/4, and after 1 bite we were at 1/2. After 2 bites we were at 1. Doesn't grow very quickly. After the 3rd bite we were at 2. The 4th bite we were at 4. The 5th bite we were at 8. And by the 6th bite we were off the chart. So write an equation that models the situation. What do we need to know to write an equation? Need to know an A value where you're starting at, the y-intercept, and you need to know your common multiple. So in this situation, what are we starting at? 1/4. And what's our common multiple? By what amount are we multiplying to grow by? And we have our exponent representing that we repeat this 2 multiple times. Remember, this is not the same thing as multiplying 1/4 times 2 and raise that to the power. That would be 2 times 1, which is 2 over 4, which is 1/2. And you repeat 1/2, you're going to shrink. but these numbers are increasing. So that helps remind you that you cannot multiply before you do your exponents. Does the graph approach but never reach a value? It does not reach anything going upwards. There's no asymptote going up. You can always get bigger. You can always take more bites, so it doesn't reach any vertical asymptote. But there is a horizontal asymptote, again, here at 0. Now, it doesn't make a lot of sense. You can't take negative bites, but mathematically, we would have a horizontal asymptote at y equals 0. So, approaches the x-axis, which is y equals 0, which is our asymptote. Does this situation represent exponential growth or exponential decay? Exponential growth. We know that the A value is greater than 0. And the B value is greater than 1. So we know that this is exponential growth. So looking at our comparisons, we have an exponential growth model. That's y equals a, b to the x. Remember that a must be a positive number, and b must be greater than 1. The graph of an exponential growth is always going to curve upwards to the right. Mathematically, it does continue here in the second quadrant as we get closer and closer to the x-axis, but we never hit it. Exponential decay is the same model. Where a has to be a positive number, it has to be greater than 0, and the b value is going to be greater than 0, but it would be less than 1 if it was exponential decay. And in this situation, the graph is going to decrease to the right, never touching the x-axis unless there was some sort of translation. Both graphs have a horizontal asymptote at y equals 0. We do have a third side. It kind of just reinforces things that we've already talked about. We have our exponential functions, which is using this format. The A value is your starting amount when x is 0, and the B value helps determine your growth or decay factor. If it's greater than 1, it's growth. If it's less than 1, it is decay. Exponential growth is when A is greater than 0, reinforcing that, and if it's growth, the B value is greater than 1. Exponential decay, the equation looks exactly the same. The A value is still a positive number. The B value is still a positive number, but it is less than 1. It's between 0 and 1. So if we're looking at a table, we can determine an equation. What do we need to know to determine an exponential equation? You need to know an A value. And the A value is what? It is your y-intercept. And the y-intercept is figured out where x is 0. In this case, our y value is 2. Then we need to know something else. The b value. So how do we determine what the b value is? If we take a look at our data, you could work backwards. You could work with the 2592 and divide out the 432, or the 72, well, the 432 divided by 72. No, 72. That is 6. You could take the 72 and divide by the 12. You could take the 12 and divide by the 2. So those are ways that you can find out. You can kind of work it backwards. Or you could look in here and just think about 2 times what number makes 12. And then you're timesing by that 6 each time to get your next value. So you know that your B value is going to be 6. We're multiplying by 6 each time to help us fill out our table. And that has to be raised to a power of x. This is not the same thing as 12 to the x power. 12 squared is 144. When x is 2, that's not 144. Not the same thing. Is this considered growth or decay? This is a growth function because the b value is greater than 1. For our second table, what's our equation going to be? What do you need to know to write an equation? This time we're still looking for where x is 0. This time it's not at the very top. You got to pay attention to where the x is 0. The y-intercept is an x is 0. So yes, that's 27. And it may be difficult to tell from the top, but if you look down here, we're dividing by 3 every time. So that's the same thing as multiplying by 1/3. You could test that out if you needed to. So our common ratio is considered 1/3, and that's to the x power. So this would be exponential decay because the b value is less than 1 but greater than 0. All right, for this next one, what's different about this letter C?
Does it have a y-intercept?
We don't see the y-intercept, but if we continue our pattern, here we're multiplying by 5 every time. So you think about it as going backwards. That means you're going to divide by 5 every time. For x to be 1, we divide the 25 by 5 to get 5. And then to get to the 0, you would divide the 5 by 5, and that would give you 1. So our equation is going to be y equals 1, 5 to the x power. You don't really even need the 1. It's just y equals 5 to the x power. This would be considered exponential growth because the common ratio is greater than 1. If we have an equation and we're going to write a table, we would need a list of x values to use. And when we plug 0 in for x, any number, happens to be 2, to the 0 power is always going to be 1. So 8 times 1 is 8. And then you're going to times that by 2. You're going to get twice as big, and twice as big, and twice as big. You're doubling with that common ratio. So that means you're going half the size. So at -1, the -1 tells you to put it into a denominator, which is 1 over 2. So you're taking half of the 8, which is 4. This would be exponential growth because the common ratio is greater than 1. And then our last one, if we use our same x values, when x is 0, we have a value of 1, so 20 times 1 is 20, and we're going to take half of it once, half of it a second time, and half of it a third time. So using that pattern, we see that we're doubling going to the left. A negative exponent would flip the fraction over, so it's 20 times 2, which would be 40. This would be exponential decay because our b value is less than 1 but greater than 0.